This is Robert Perkins. This is the final project on deep learning with data on convolutional neural networks, adta5550. And this is December the 12th. What I'm going to cover is about the final project, and this is going to be on parts 1, which is the fruit image for object detection. This is the data that we're supposed to find ourselves and do some analysis on the data. And so I'll talk to you about that as well. On part 2, this is the SciFar 10 data set, and this is the data set that we used. And so we'll go through that data set as well. And then on part 3 is where we build, train, and test the convolutional neural network for the SciFar 10 data set. And then part 4, and that's where we'll compare the convolutional neural network performances between between the neural networks. And then part 5 is where we'll look at where we made some improvements to the convolutional neural networks and see what those test results are. And then at the end, we'll do some conclusions on what we found, what we learned around these particular convolutional neural networks. So first, this is the fruit image for object detection. This is the data set that I found on Kaggle, and it has in the training files, there's 240 images as well as 60 labels. And there's also 240 images and 60 labels in the test files as well. The height and width of the image varies. It varies when we took a look at all the different images. There were different variances, height and width on those. The entire file size was over 30 megabytes. The data file itself had 3 classes of outputs for the labels. There were apples, bananas, and oranges. The images were color, which means that it had a depth of 3, and it had full color with RGB. And as I stated earlier, the website where the information or the actual images were found is on the Kaggle, and attached here is the actual website and the link that you can go and click on it to find those data sets for those images as well. Part 2, the SciFar data set. This particular data set, this is where I'm showing you the steps that I took in order to get access to the data. I actually downloaded the file from the Canvas site, the UNT Canvas site for a class. There were, there's actually, the file itself was actually zipped. And there were, within the zip file, there were 7 files that were actually zipped within the 7 files. Once I downloaded it to my local personal computer, I logged into the GCP console and I started up a VM under the compute engine within the GCP console. I opened a SSH connection browser, which connected my local computer with the GCP console. So then I could actually upload the actual file from my local computer to the actual virtual the VM. And then what I did was once I did that, I actually went to the VM directory, which is my user ID, and I within the on the GCP console, and I created a folder within the JP underscore NTBK, which is already there. I created an additional folder, which is the SciFar dat underscore 10 underscore data. And then we were instructed to do this, to create the subfolder as well. So then I clicked upload the file, and the file was actually uploaded. Once the file is uploaded, then I was able to use the uh, uh, the unzip command to actually unzip the file, and that's where the 7 files were actually unzipped. Then what I did was I copied those 7 files from the main VM root directory. I copied those to the actual directory, the SciFar underscore 10 underscore data subfolder, which is where we were instructed to actually put those files. So those 7 files were there. The 7 files were the data underscore batch 1 through 5, and then the actual batches dot meta, which had all the labels, information in there, the different labels, and then the test batch file, which had all the test images in there, as well as the label images, as the labels, I'm sorry. Then the next thing we wanted to do, after we loaded the files, we wanted to actually build, train, and test a convolutional neural network uh, using the SciFar 10 dataset. And what I wanted to do here first is I wanted to give you just an overview of what is going to take place, and then we'll walk through the steps. But this is a block diagram of what you can expect when you're building a convolutional neural network for deep learning. Uh, so you see block 1, this is the input data. This is where you have your in this particular case, this is where our images as well as our labels for input is actually in the input data. That is actually the training images are fed into the model, and we'll go through the model in the next slide. And then we'll talk more about that. And then the next block diagrams we'll go through how you process the images, and once you go through in a convolutional neural network. Here is a deeper dive into that block 2 that you saw with the convolutional neural network. Here, this is where you see the actual here for our particular SciFar 10 data set. You can see we had a 32 by 32 image. That's the height and width of the image for each one of the images. And then these were color images. So these images had a depth of 3. As these images are going through, the first layer that they go through is a filter. We use a 5 by 5 filter that actually filters and get the most important features as it's going through the actual entire image. And then once it goes through and get the entire features in the filter, then we send it through we send it to the next stage, which is the next layer. We use in the convolutional, within the convolutional layer as well. When it gets through the filtering, we actually use a activation fund, which is the ReLU, and that ReLU really is a function that help us determine whether the feature, what should be the probability of the feature. Once we do that and we sum those features up, it goes through the max pooling. The max pooling is where the actual then we actually take the image and it is actually reduced down to size. In this particular case, we're using a stride of a 2x2, and so it's going to be reduced down to half. And so you can see, instead of it being a 32 by 32 image, now it's a 16 by 16 image after it's gone through the first pooling layer. And then we use a second layer, and it goes back through filter again. Once it goes back through a 5x5 filter again. Once it goes through that filter again, then repeat the process that it went through in the layer 1, but this is just layer 2. And so once again, we have a ReLU activation fund, that activation function that takes the probabilities and then it determines which features are significant. Then that is moved over. Then that is sent over to the max pooling again, which is actually then it looks at those significant features, and the ones that are not, it discards them, and then it reduces the image again in half again. And so now in a 2-layer operation, we're down to an 8x8. Then before it goes into the fully connected network, it is flattened into a 1-dimensional, because before it was actually 4-dimensional. But it is flattened to a 1-dimensional. And in this particular case, we've got an output of 3072 pixels, because it's a 3-dimensional. It's actually 4-dimensional, but 4th dimensional is none. But the actual depth, and so in each one of these colors, we've got 1024 pixels. So we've got an output of 3072 pixels that's flattened into a 1-dimensional. Then that goes into the fully connected network, and within there's actually a drop layer within the fully connected, as well as a ReLU. It goes to the ReLU first. The first fully connected network goes to the ReLU. Then it spits out the outputs from there, which tells us what the weightings should be and the biases, and then it multiplies those out in the multiplication function, and then from there it take those and add the biases, and then it goes to the next layer, which is a dropout layer. And within the dropout layer, what happens then, it actually takes the output, and then from there in the output layers, it determines that it drops 50% out. And the reason why we drop 50% in the dropout layers, because before we go into the last fully connected network layer, we want to make sure that we're not putting too much data in there once we go to training, so that it is so then it's not overfitting the data. Okay, And then once it goes to the output, and then the output, we've got here in this particular case, we do a one-hot encoding, where we've got where we do in the one-hot encoding, we have an output depending on which type of image it is. It will be a one hot coding. It will have a one under that particular image or label. Okay, here in part 4 is where we compare the convolutional neural network performance, the accuracy of the MNIST data set with the SciFi-10 data set. As you can see, the MNIST accuracy performed, in the well over almost 98% across pretty quickly. Once it got up to about 600, it was in the high 90s from an accuracy perspective. When I compare that to the SciFi-10, you can see that it was in the mid 60% from an accuracy. So there is a difference between the two on the accuracy. And you can see that's about 30 basis point difference between the two. Now I compared in part 4, I also compared, I did an improvement to the SciFi accuracy by adding 2 additional convolutional layers to see if we could get the increase in accuracy up. But as you see, it performed about the same, and as it did with 2 convolutional layers. We also added, and I'll talk more about this, in our conclusions. But we also added, we went from 5,000 steps to 10,000 steps. But what we found that the accuracy level went down, and we think that that was due to probably some overfitting in the testing data. It actually decreased. So we didn't get the same amount, or we didn't improve the accuracy, should I say. So therefore, it didn't help us by in adding the 2 additional convolutional layers. Also, when we added the additional steps along with the convolutional layers, the processing time dramatically increased. And so it actually caused us to abort the actual the program as it was going through the convolutional neural networks, because at the rate that it was going to take probably over 4 hours to complete. And so as we'll talk a little bit more about that as we move forward. So improving the convolutional network performance, as I talked about, we added, two convolutional layers with the ReLU, as well as pooling layers. We increased the training steps from 5,000 to 10,000, which when we did that, it really increased the processing time. And so we had to abort that. We also increased the learning rate which really didn't make um, that much difference in the actual accuracy level. We also tried, changing the size of the filters, but uh, that really, we got a decline in our accuracy level when we did that. And then we tried some combinations of the above, and so we had to be careful there because some combinations led to really high processing time, so we were not able to finish those out. One of the things we talked about is, maybe, if we had some, increase in the number of images that we could train on, then we could probably improve uh, the uh, the accuracy levels as well. So in conclusion, what did we find out? What did we learn? Well, we learned that the Manis, you know, data set was a much simpler data set. It was black and white image. It was a 28 by 20 smaller, but I guess the biggest thing is it was a one dimensional. It The actual images itself were just single digit 0 to 9, so it wasn't a very complex uh, image. And then really, when you look at it, it's pretty straightforward and simple. Now, when we look at the SciFar 10 model, you can see that it was a much more complex uh, image. There were 10 different objects, from animals to, to vehicles, to airplanes, to trucks, um, and, and different animals like birds. Uh, and so, when you've got that many, different objects, and there's, features, significant features everywhere. There's also, we had the, it was three-dimensional, which means that it had the RGB colors, which also increased the complexity as well. So once again, the SciFar image was a much more complex, which would lead you to believe that the accuracy level on, recognizing the image would decrease from the simpler Manis, which is what we saw. As we talked about, the additional layers and the training step added significant processing time to the overall uh, convolution networks as we were going through the training and testing steps. The the time was much more. It was probably, to the tune of, from a half a second a second prior to adding the additional training steps and layers to about 20 to 30 seconds per, you know, um, 100 batches. So with that, that was a significant amount of more time. As we talked about, we would, propose to include more imaging for training. The other thing we would propose that we could, instead of, in this particular on the GCP platform, we use the GPU, which is a graphical processing units. We could have, gone and increased it to the TPU units, which is a tensor processing units. Tensor processing units process about 15 to 30 times faster than the GPU, which would have given us a lot more, processing power, and therefore we could have really, pushed the limits of our testing and training and testing by adding more steps, as well as adding more layers as well. And we believe that had we done that, we would have gotten, the accuracy levels um, up by being able to do that. Also, we talked about this as well about getting, there's some opportunity also to use more some of the, optimizer, using different optimizer as well, which you know, decrease your time by arriving at your loss, or minimizing the amount of loss you have between training cycles as well. As we talked about, and that's the 15 to 30